All right, we want to be able to discuss the relationship between a distribution of x and a distribution of the standard normal curve. Remember that the standard normal curve is very nicely distributed around a mean of 0 and a standard deviation of 1. This is very nice for us because it means that we can discuss the distribution pretty much based between a range of -3 to +3, and that's very, very helpful. But as we know, x does not correspond with those measurement properties. So if I have just a value of x, I want to be able to discuss where x is relative to its mean with the utility of discussing the distribution in standard normal curves. So I want to be able to force the distribution of x to have a mean of 0 and a standard deviation of 1 as well. And the way that I do that is I compute z-scores from every value of x. So once I have a value of x, I can subtract mu, which is what we know about the population mean, and divide by sigma. In this way, every value of x can be assigned a z-score, and a z-score is interpreted as a unit of standard deviation. So if I have the population distribution information, meaning that I have mu, the population mean, and I have sigma, the population standard deviation, I can compute a standardized score for every value of x. So if I know, for example, that a z-score is 4.5, if I draw that distribution, okay, the z-score of 4.5 is going to correspond to a value of x that's 4.5 standard deviations away. Okay, so here's 1 standard deviation away, 2, 3, 4, 4.5 standard deviations away. And I know that that is extremely unlikely, given what I know about the probabilities of various areas under the curve. Only about 2% of the distribution is going to be beyond 2 standard deviations from the mean. So I know that 4.5 standard deviations is very far away. If I know that the z-score is -3.4, then that tells me that it's going to be about 1/3 of a standard deviation below the mean of a distribution of x. And that is a very likely observation. To the extent that scores kind of cluster around the mean, they're more likely. To the extent that they kind of get out farther away from the mean, they become less likely. Now, remember, using Table A, we can solve for various types of probabilities. These values here refer to values of z, and as I look to Table A, okay, those z values are going to correspond with different points along this axis. And then I need to be able to tell whether I'm solving for example, this area, okay, the mean between the mean and a certain z value. Remember that z values, okay, are in units of standard deviation. So when you look at that table, it's going to be expressed in terms of what the sigmas are, but that corresponds to a z-score or a standardized score. Likewise, if this is my observation here, and I want to know what likelihood of the distribution is beyond this value, I know I'm looking for this area. So you really do need to practice using the z-tables in order to solve these probabilities. So just to say, if I want to be able to calculate a percentile for a positive z-score, okay, and my z-score is 0.98, okay, I need to be able to solve for this piece here, as well as add the bottom 50% of the distribution. So looking at those tables, I can see that 50% of the distribution is below the mean, and I know that if I have a sigma value, of 0.98, that's going to correspond to about 33.65% of my distribution. So remembering that a percentile is the point at or below a given value on the curve, I can see that 50% plus 33% is going to give me about 83.65% of my distribution is at or below a z-score of 0.98. If I want to calculate the percentage above a z-score, okay, remember that in the textbook these are called sigma values. Sigma values is synonymous with a z value. Okay? If I want to calculate this portion, okay, or the percentage of the curve that's above a certain sigma value, then I look at a different column and I see that that's 16.35%. So I know that, for example, the probability of obtaining a z-score greater than 0.98 is only 16.35% likely. And I can do this same thing for a negative z-score. If I want to know the percentile for a negative z-score, I know that number one, I'm dealing with the bottom end of the distribution. Okay? And a percentile is the point at or below a given score, so I know I'm looking for this piece. That's going to correspond with an area of 3.44%. If I want to know the percentage above a negative z-score, okay, then I have two pieces that I have to deal with. First, this piece, which is always going to be 50%, and then this piece, or the point between my sigma value of negative 1.82 and the mean of the distribution. Looking in Table A and Appendix C will give you these different probabilities, and you'll need to practice those within the Revel text.